The experiment was conceived in 2003, something like that. So in about 2.5 years, we had the first telescope. The leftmost is in a factory in Bangalore that we brought into Hadley. And as I told you, there's 7 mirrors, and you can see in one of them the mirror, and actually there is a photo multiplier sitting at the focus. As I told you very early, this is a traditional method now, and so here that one with the heart gives you an idea how big it is, and then the other one that it is in the Himalayas. Now, as I told you, the most important thing actually of these experiments is what energy it will, what will be the minimum energy, what we call thresholds. Like most of the Cherenkov experiments are about 2 to 300 GeV and they had stopped there. But as I said, we hope that we use the aspect of high altitude, and our calculations show that the thresholds could be as low as 60 GeV when everything works out. And these are some technical information, and I will skip that. Another point is the angular resolution. Astronomers always talk about that. Our angular resolution is good for gamma ray storm. It's not good from optical standards. We do not worry about that because Cherenkov actually is not it's a cone type of thing. So 0.2, 0.3 degrees are supposed to be quite all right, and so that's what we hope to achieve in this experiment. And how do we get angular this thing? But essentially, it is we collect signals from all the 7 telescopes, 7 mirrors, and that is how we what's called triangulation, which I won't go into now. And this is the energy spectrum of Crab Nebula, and what is showing is results of many experiments. This is the left-hand side shows the intensity in subunits. The y-axis, sorry, x-axis shows the energy, and this is by various experiments. And this is our latest, what we call the preliminary result, and it seems to agree quite well with what is expected. As I told you several times, we have to do Crab Nebula so that we know the instrument is working, and this is a very decent result. And now this is the actual, wait, okay, sorry, all right. Now this is the ARTIS U about 2007, but this is what it looked like in 2008. You can see there are 7 telescopes. The actual optical telescope is at the top of the hill. We are slightly lower by about 2 to 300 meters, and this is the same scene in winter. So these are 7 Cherenkov telescopes, and we call this Haggard. This is, as I told you, working in Hanley in Ladakh. People are welcome to come and look at it, and especially if you are in the field of any astronomy, please come and participate. And what we are doing now is we are taking what we call data, and now I already told you that Crab we seem to be doing all right. So we are now looking at several interesting sources. Our idea, as I told you, is if we are coming around 100 to even 100 GeV, we can do very good work. And the Pachmari and Mount Abu, the experiments are slowly fading, and now this is the big thing in gamma ray astronomy in our country. The next big thing, which is going to be MACE, which is a huge telescope, 21-meter diameter, about 400 square meter, I think it comes to. That will also be spent in Hanley. And this main initiative is by BRC, Bhabha Atomic Center Group in Mumbai. And they will have the lowest energy possible, competing with satellites. And when this comes up in about 2 3 years from now, this will probably be the best gamma ray telescope in the world. And this is, as we said, the second stage. First, Haggard was the first stage. This just gives you some details about how big it is, etc. And so it's already kind of civil works have started in Hanley. Okay, simulation means calculations. We have to simulate because we do not know what the reality is. So we assume certain things at around 30 GeV per base, which is very good. And, so the very ultra, now I'm going to get straight into another field, ultra high energy gamma ray experiments. I won't say anything more. I've already showed you the experiments in Tibet and Ooty. So the same experiments are used for gamma ray work. And they use certain methods. I'll skip that. And what I would like to talk about is due to just very short. This thing I won't be able to talk much at all because neutrinos are really very exciting particles. And this is, for example, as some of you may know, The most elementary particles are essentially quarks and leptons, and neutrinos are leptons. Okay, and these most physics students know how this was came out because of Pauli, this particular idea. And today, neutrino, I will just want to show you one or two plots here. Neutrinos are kind of ubiquitous particles. They are everywhere in the universe. And the most important thing, which, for example, which happened in the last 10 years is from Sun, the neutrinos have been found, and it shows that the age-old theories have been proved very correctly. So it's a solar part of solar astronomy, but it's also formed by supernovas, which are supposed to give neutrinos. Now let me just skip here, and this is, for example, I already showed you 1987 supernova, and I showed you the optical part, but here are the neutrino thing. You cannot go deep into these graphs now, but 3 experiments found signals of neutrinos, and it showed that all the supernova theories were very good. And the last thing about neutrinos, which I would like to say, is just like gamma ray astronomy at very high energies, one can also use neutrinos, because neutrinos come from the sources directly, and at least gamma rays are absorbed, but neutrinos are very weakly interacting particles, so nothing is absorbed. So I'm sorry I will not be able to do much justice to it, but I'll just show you one very interesting experiment which is taking place now in Antarctica. It's called IceCube, and below ice they have put a photomultiplier. By now you know what a photomultiplier is, and they look at the interactions of neutrinos, and this experiment is supposed to study neutrinos from objects like active galactic nuclei and all that. I'm sorry I could not do much justice to the neutrino part, but also I should tell you that in India also very famous, very important experiment is going to come up called the INO, Indian Neutrino Observatory, somewhere in Tamil Nadu, and that will also contribute to neutrino physics and astronomy. So this I end, but I would just like to say that very recap of whole thing, like that what we discussed was essentially very high energy particles. We first talked about cosmic ray charged particles. Now the question was where are they coming from? Then again the question is then to follow 20 electron orbit, how do you get it at all? And the second thing we talked about is, for example, the gamma ray astronomy. The photons or ultra energy photons, how are they made, and where are the objects which are giving out these ultra energy photons? And the very important thing which we were not mentioning occasionally is that the multi-wavelength aspect. That nothing can be done today with studying in only one optical or one gamma ray, everything you need. So I hope that is the kind of if you take home that particular aspect, the multi-wavelength astronomy is the most important aspect today for astronomy, I think, but I hope that when you use this, and you can go on to there's much deeper aspects. Obviously, we cannot talk about those things. The link will be given. So I thank the Nehru Planetarium for giving me the opportunity to talk to you about this. Thanks.
Thank you, Professor Shah.